So hello everyone, my name is Richard Lobianco from Scottish Carbon and Capture and Storage. I'm very happy to welcome everyone to today's webinar. This is a project's 6th webinar overall. It's the 5th and final webinar of our 5-part autumn series that we started in mid-October. I'm very happy to introduce today's topic, which is onshore CO2 storage in Spain, presenting an overview of geological, technical, economic and social assessments. So without further ado, I'd like to hand over to our first speaker today, who'll give an introduction, Paula. Paula, the floor is yours.
Thank you very much, Richard. Good afternoon to everybody. Thank you very much for joining us in this last webinar dedicated to Ebro Basin region in Spain. This is our agenda. As you will see, we have between 5 or 10 minutes from different topics. We cannot cover all the work that we have done, but we invite you to visit the webpage of the project, the pilotstrategy.eu, because you can find there all the deliverables and reports that we have been producing so far. So I will start here presenting you the Ebro Basin core team. All of us will be there in the last 20 minutes for questions. I have to say that this is only the core team, and there are many colleagues that they are working with us in many different activities, but there is not enough space for all of us because we have few colleagues working on this, and we would like to thank all of them for the really amazing work that they are doing. So I will start with this general overview of the pilot strategy. I'm Paula Canteli. I'm the coordinator of the Ebro Basin work. I'm working on the geological survey of Spain. And if you have been attending to the previous webinars, you will see before, you will have saw before this, but anyway, we need to go through this. The pilot strategy is a funded project by the European Commission Research and Innovation Programme. We have a budget of 10 million for 5 years. We started in 2021 and we are in the last part of the project. In total, the consortium is 21 partners and was mandatory by the Commission that this consortium will be research organization and also industry, to have this path to the commercial implementation of the CCS technologies. And that is the last objective of the Commission, to promote and implement the CCS implementation in the south of east of Europe. And in particular, in this project, we're looking forward to prepare a pre-investment proposal that is a set of recommendations for going ahead or not to 3 pilots, one in Paris Basin in France, one in Lusitania Basin in Portugal, and one in Spain in the Ebro Basin, and also a set of recommendations for next steps, but more general in the case of Poland and Greece. We are working in deep saline aquifers for all the different sites in the project. It's important that you keep this in mind. The pilot strategy, we understand that for the implementation is really important, the technical side, but not alone. We always approach from a multi-criteria point of view, that is the technical evaluation, environmental risk, social acceptance, techno-economic evaluation, social-economic evaluation, and the legal frame and incentives. And with all of this, we have organized in this work package, the geocharacterization, what we understand the subsoil, and we finalize with the geological concept for each site, the modeling, first the static and then the dynamic modeling and the dynamic simulation, the 2 big pillars, the work package, the safety and performance, and also the social acceptance. And we can analyze all of this with the pilot development and implementation with the last investment proposal. We have to say that the final objective is not only these recommendations. We want also that all that we produce, guidelines and report, can be a model for future investors and operators. We want to identify, and we are doing gaps for CO2 storage implementation in the regulation and legislation, and we want also to build confidence in society, including citizens, administration, investors, and operators. Thinking in the Ebro Basin itself, in the work that we are doing in Spain, you see here, I forgot to mention that the Ebro Basin team is, the organization is the IGME, the Geological Survey, CIEMAT, is other research organization, Spanish research organization, and Repsol as our industrial partner. And we organize the work, as you see, in some cases, leading one and with the support of the others. Ebro Basin is the only one region that we have asked specifically for a socioeconomic evaluation, that is to evaluate and understand the impact of a potential implementation of the CCS in the area, in investment and jobs creation. Going through the Ebro Basin itself, we start the project, if you have been in the previous, the same that Portugal, and it's different that in the case of France, proposing two different sites, one onshore and one offshore. And with the idea of on the month 18, that was in September 22, to select one of them and follow the rest of the project focused in only one of them. The onshore was proposed by IGME based on the work done previously, in the Algeco project mainly, and the Strategic US project that was previous. And the offshore was proposed by Repsol based on the information that they have for this area, because this area corresponds an area where was in production, oil and gas production during more than 50 years. However, keep in mind that we are talking about the saline aquifers. They have a lot of data because they have been working there, but now we are focused on the saline aquifers. Something that is really interesting is the two sites were absolutely different. Different geology, different number of quality of data, different industrial possibility and needs for emitters from the industry in the area, different potential of existing infrastructure, on-grid infrastructure was absolutely different. So we have been during the first month compiling all data that was possible with the idea of taking this decision. So we initially collect this data and try to identify pros and cons for both sides, and to go through these key criteria and try to evaluate first if it was possible in a qualitative way, because with a short time we thought that if it's possible it would be great, if not, quantitative. The first idea was also to identify stoppers. If we have one stopper in one of these key criteria that could take the decision early, but it was not. So at the end of September 22, the Ebro Basin team take a decision, and this is really important to say that we all agree and go with the same selected site. And before going this, that is only one of the samples that the work done led by CIEMAT, the environmental risk assessment. As you see, we were identified different barriers that prevent for the CO2 moving to the top and the impact that can have on the top. It was represented with a spider diagram. You see there is no really big difference between them, and all together with other type of diagrams. And the important conclusion was that both sides was equally valid from the environmental risk assessment. And that happened also for other technical criteria. So at the end, that is the point, we decided that the onshore site, that is our Lopin site, was the one selected. And if you see in the first one, from a technical point of view, both was equally, so no different, really difference. And also for the social acceptance, it's slightly more favorable the onshore, but really at this point, it was not enough for taking the decision. The really decision, and all of us agree on this, was the other points. The onshore site was more chance of progressing because of the lower cost, simplicity in development, operability, monitoring, and easy regulation. Also because the direct impact in the investment and in the job generation, higher visibility towards society and institutions, and really important in the case of Spain, because we have around 100 potential structures to be implemented for CO2 storage. It was the replication that the work done on the onshore. So just my last slide is our Peñarroya Cinteruel, is our analog, one of our analogs of Lopin. That is, Jesús will explain the geological model. But perhaps you are asking what happened with the offshore work that we have been done during these 18 months. And Francisco, our next speaker, we will explain you about that. So Francisco, I will give you.
Thank you, Paula, and good afternoon, everyone. So, as Paula mentioned, the criteria for selecting the onshore was based on a series of factors, one of them being the ease to implement the pilot and the difference in cost. But Repsol kept actively evaluating the offshore, and I will show the rationale of why we did it. If we look at the Spanish industrial emissions map, which is in this small insert in the bigger map in the slide, we can see that we have some 60-something million tons per year of CO2 emissions from industry. And if we consider those and only keep the sources higher than 0.4 million tons per year, we have 25 million tons per year of emissions from industry that is in most cases hard to abate, and that are eager to implement the carbonization measures. We meet with these emitters and they tell us we can optimize, we can implement energy efficiency, change our feedstock, but there are emissions that are still there and need to be taken care of. So CCS is the tool to provide additional abatement volume to these industries so that they can survive. So we analyze the geography of Spain, the distribution of these industries, and we spot the Ebro Delta area as a potential, as an area with potential for a CCS project. We identified cement and chemical industry in the vicinity of a very expressive delta that I will show in the next slide. The Ebro Delta is unique in Spain. It houses a more than 2 kilometer thick sedimentary pile of Miocene age, housing very good reservoirs, and it was affected by a peculiar geologic event that is the Messian desiccation event during the Miocene that resulted in the configuration of a very favorable context for CO2 storage in saline aquifers. Here in the central seismic line, you can see the thickness of the delta sediments, and in red with the light blue arrow, the Messian unconformity that provides us with the trap and the seal for our CO2 storage. In the next slide, thank you, Manuel, for pointing out, we can see a detail of our intended storage site. Here we are seeing a series of sandstones. It's some 500 meters of sandstones with 100 meters of net reservoir, very good quality. As Paula mentioned, Repsol has been operating here for more than 30 years. We drilled successfully more than 17 wells and operated a platform that is now in decommissioning. So we have a lot of information and knowledge of the area. What we were able to identify is some shallow marine reservoirs in a multi-story reservoir unit that, if you look at the image from on the right-hand side, it's very colorful and appalling. What is showing is, with a north-south orientation or vertical orientation, is a series of shallow marine sands, like being on the beach. And these stripes you see crossing perpendicularly are fluvial channels. This is the way we are imaging the reservoir of our storage. In the next slide, we can see one of the benefits of having this kind of reservoirs. we build our static model to characterize our storage, and we run dynamic simulations. What would happen with the CO2 after years of injection? What we are seeing here is a focus on the reservoir unit. Our engineers modeled the injection during 30 years, and what we can see is that thanks to this configuration, this geometry of the reservoir, the CO2 plume does not extend much. It extends some few kilometers, less than 5, away from the wells. And this configuration also favors the immobilization of the plume. That supports the interpretation of the potential for a permanent storage of the CO2. How do we prove this? And this is hypothetical. If we happen to develop, we get to develop the project and we get to store the CO2, then there are a series of activities that we will carry out to make sure that CO2 stays there. And that is through the MMB plan, that is measuring, monitoring, and verification, which implements seismic methodology, geochemical sampling, and all kinds of geophysical surveys in the sea bottom and on the wells to guarantee that the CO2 stays there. Last, this Manuel. So why did we choose offshore Tarragona? Because there is a concentration of hard-to-abate industry that has emissions that need to be taken care of, and it's not enough to them with energy efficiency. They need to go beyond that. We have a very favorable geologic context, which is very appalling for CO2 storage. And we have that combined with the operational experience of Repsol that has been there operating for many years and drilling safely and in a good relationship with the stakeholders, the local stakeholders. So that is why Repsol applied for the Tarraco investigation permit. What we want to do is to investigate the feasibility of CO2 storage. And recently, we were awarded the innovation funds by the European Commission, that we are in the process of signing the grant agreement, and hopefully we will see a project sometime in the future. Thank you very much.
Thank you, Francisco. I was happy that you say at the end that you have asked for the permit for those that they are no Spanish. Thank you.
Thank you. Thank you.
Jesús will present now Lopin geological model, please.
Yeah. Hello, everyone. Continuing with the onshore side, I will briefly explain the conceptual model and the step we have followed to build the geological model included in the work packages 2 and 3 of the project. In summary, from already existing data, such as seismic sections, wells, or literature, and from new surveys like gravimetry, seismicity, the study of analogs, outcrops, or photogrammetry with drone, we have obtained a conceptual model that includes the petrophysical characteristics and the results of the phases analysis and the geochemical and geomechanical assessment. In work package 3, the model is built following a workflow that includes an interpretation of the seismic sections, the analysis and trends of the data, the study of the uncertainty, to first build a model with the reservoir properties and then a grid model ready for dynamic simulation. The conceptual model comprises a sequence that begins on a metamorphic paleozoic basement and is made up of a Mesozoic series composed of the Triassic, Jurassic, Cretaceous, and the Cenozoic on top. The formation of interest in the Ebro Basin is the Triassic, specifically the so-called Bunsenstein sandstones, which is divided into 3 members called B1, B2, and B3 for these, with members B1 and B2 constituting the reservoir and B3 the cap rock. B1 would be fluvial sediments of braided type channels interspersed with floodplain shales mainly, B2 would be sediments of a meandering river system, and B3 would correspond to marine type shales and marls and act as a primary seal. Above this formation are the musical and Kuiper, and other formations that could act as secondary seals are the middle musical member and the Kuiper faces. Then from the conceptual model and the interpretation of the seismic sections, and with support of the other data, we have built a three-dimensional structural model using the structure and stratigraphy workflow. This structural model revealed a deep horse and gravel type structure with a closure at a depth of about 1,650 meters below the sea level. From the structural model, a cell model was built using the square grid workflow in which to populate the petrophysical properties. Then the population of these petrophysical properties is conditioned by the distribution of the heterogeneities existing in the formation, both vertical and horizontal, with alternating superimposed channels with variable orientation and density. This spatial variation can be characterized from the study of some wells, outcrops, and examples of the literature on current fluvial sedimentary environment. Two phases have been differentiated, channels and non-channel phases or shales, considering 8% porosity as a cutoff value. As there are countless possible combinations of channel distributions, we run several simulation uses using the FlowSim workflow and Gaussian simulation to find a combination of channel parameters, that is proportion, orientation, sinuosity, etc., that reproduces the statistical distribution of the porosity in each of the members of the formation. So the goal was to reproduce the reservoir heterogeneity. Finally, we obtained a three-dimensional phase distribution model. Each phase has a statistical distribution of porosities, honoring the one obtained from the wells. Here you can see the general orientation of the channels and the distribution of the porosity within the channels and within the shales for the member B1 above and the member B2 below. The permeability and the shale volume properties have been calculated from a theoretical correlation with the porosity. And the last step was to make an estimate of the final volumes available for both the whole area and the area of interest, the pilot site, where it's proposed to install the pilot injector project. In this case, it's a smaller area with a estimated capacity between 7 and 23 million tons of CO2 under the pressure and temperature conditions calculated for that depth. So this is all from my side. Thank you for listening. And now I give floor to Manuel Bron, who will explain the dynamic modeling and the subsequent tasks. Thank you.
Hello, good afternoon, everyone. So I'm going to explain the onshore CO2 storage possible development. So once we perform the static model, as Jesus said before, it's time to build the dynamic model. What is this? The dynamic model, the objective is to simulate the CO2 behavior through time and in the reservoir, I mean in the porous media. In this case, our Triassic sandstone are at more or less 1,800 meters depth, okay? So with the dynamic model, we will answer questions. For example, the first one is, what is the maximum capacity that I can inject in our reservoir? What is the time that I need for this? At which injection rate I can fill my formation? And each one of these steps needs, of course, a geological characterization that was done in the previous steps. We need to know perfectly the reservoir conditions. I mean, the temperature, that is the geothermal gradient, that is the increase of temperature with depth. Here in Lopin area, in Ebro Basin, is only 3 degrees per 100 meters, and the reservoir temperature is close to 70 degrees Celsius at the reservoir depth. And the pressure is something very important because below 800 meters, the CO2 became supercritical. What that means? That one of the meanings is that CO2, you can compress it more than 3 orders of magnitude. And the CO2 will behave a mixed behavior as gas and liquid. Then we need to assess the geomechanical properties of our rock. This geomechanical assessment will give you a lot of answers, but the main one is what is the limit, the highest pressure that I can apply to my reservoir? What is the injection pressure, the maximum injection pressure that I can apply? Okay. For this, we take these rock samples, as you can see in the screen, and we can take it in the surface, as Paula showed before, this outcrop, or in the old wells. Another way to do it and to match the results with the laboratory test is just to take the well logs that you can see in the bottom. That is some data that you can take from the drilled wells. That this data characterize the type of rocks that you have. Okay, so after this we need to make some rock fluid model. Why? Because the CO2 will interact with the rocks and with the fluids inside of these rocks. For example, another thing is the CO2 that you are going to inject is not pure. You have a certain percentage of impurities that you need to know what is it, what is the chemical composition, because with this you will more or less know, you will know what is the reactions that would happen at the reservoir level, okay? Some tests that we can do is static tests. What does it mean? We take a piece of rock, we put it in contact with CO2 and with formation fluid. And with this, you can measure the chemical reactions that happens there, okay? And another type of test is just to force a CO2 to flow through a piece of rock, through a piece of rock, and see the results and measure properties like the relative permeability. Another important thing is the water salinity. That is part of the previous step. Why is important the salinity? As a comparison, the seawater has 35,000 ppm of sodium chloride, okay? And this, in our target interval, we have salinities much more higher than this. It's more than 250,000 ppm. That means that our saline aquifer is perfectly isolated from the surface, and with this water, that is brackish water, you cannot do anything. It's impossible to use it for any other purposes. So once the dynamic model is done, the simulator will give you some results, but it will give you, imagine that, hundreds of possibilities. So you need to adjust or to play with the parameters to see how it affects to the final results, okay? So it's important to consider the static properties, so to make a little variation on the porosity and permeability of the reservoir, to consider the faults, to consider maybe the faults are sealing and does not allow the fluids to go through them, or maybe they are communicating. You need to play with the water salinity because you don't have a fixed value. You know that it's high, but you don't know for sure. You need to vary it. You need to vary to play with the rock compressibility and with this, not to get the most realistic result that you can get. Later on, it's time to play with rates because the rate is the injection rate. You can inject 1 million ton per year or 500,000 ton per year or whatever rate, okay? So playing with these rates, you will have different reservoir pressure. You will apply different pressure to our reservoir depending on the rate that you inject, okay? So this rate will affect also to the injected in CO2 mass, okay? And for example, in the lower side, you have a cross-section, depth versus distance, and in blue, light blue, you can see the CO2 plume, okay? this plume will go further or will extend laterally depending on the properties that you have in your model, okay? If you inject low amount, you will have a smaller plume that you inject more, okay? So now it's time to place the well. You have here a surface map of the project area. Now this is a reservoir map of our target interval close to 2,000 meters. And this is the results of the simulator, okay? In light blue is the areas that we cannot go because they are protected, because there are vegetation there that you cannot do anything there. And in green, there are the areas that simulator tell us that are secure for injection at the rate that we need. And then it's time to do the long-term simulation. What does it mean? That instead of simulation for 50 years, you will simulate for 2,000 years to see and to ensure that the CO2 will be stored permanently in underground. Okay. Another thing that's very important to do is to characterize the natural seismicity of the area. For that, we put 5 seismological stations and measure during 1 year the earthquakes that are in the area. Okay. The final answer to that is that the seismicity, the natural seismicity there is extremely low, so the project is very safe. But this is something that you need to pay attention to. After this, we need to have a proper image of the subsurface. We have models, and now we have an idea, but if you have more data, you have more confidence. So we can shoot seismic with these tracks that apply vibrations to the ground and produce this kind of images that is seismic section that we interpret, okay? So in Lopin area, you have here the reservoir map. These lines are the places where the track is going to record the signal to have a beautiful and a dense network, so we will have a better and more accurate picture of the subsurface. Also, one thing that we need to do is to plan to drill the well in cost and in the procedures, because the well will drill some rocks that we need to take in account: limestones, salts, sandstones, and if each one of these rocks requires engineering, requires to study how you are going to drill them. Just for data, in Lopin, a well will cost, an injection well, more or less $8 million USD. Another thing that we have to do is the facilities or the installations. We need storage tanks. We need to drill wells to inject. We need pumping stations to apply the enough pressure to inject. We need power, okay? So with this and making sensitivities and different scenarios, you can go from $25 million to more than close to $300 million. And the scenarios, economic scenarios and project scenarios that we are considering here are 3. The first one is a minimum investment. In this scenario, we try to protect the financial risk, and we try to do this pilot project as simple and as cheapest that we can. But our favorite scenario is first of its kind. This scenario is trying to mimic another European projects that, like Northern Lights, like Porthos, or like other projects that are planified. And for this, the target is to store 23 million tons. And another possibility is to modify the previous one and obtain the energy that we need, mainly electricity, for the compression from solar panels or wind farms or other green sources. No, is to lower the carbon footprint. And thank you very much.
Thanks,
Richard?
Manuel.
Okay. Thank you, Paula.
Christian, could you share your screen? Please.
Christian, we can see your screen. We just can't hear you. You're muted.
Sorry. Yeah. Can you see the screen, right?
Yes, thank you.
Thank you. So the development of carbon capture and storage projects has taught us a critical lesson, that is that we need technical feasibility and environmental and techno-economic feasibility, but we also need to consider the relationships with the communities and the social acceptance. We know that from past experience in the CCS world, but also in other energy technologies, that some important projects fail because of reasons related to opposition from the local communities and lack of social acceptance and support. So in pilot, we have considered this very seriously in all the development of our project and of our research. Social acceptance is a critical word here, but it should be considered only a thing to be overcome, but a fundamental pillar of successful CCS projects. It means public understanding, trust building, risk communication, community engagement from the start of the project to the end of the project. But a critical idea also is that the vision of CCS projects should go beyond achieving public support or public acceptance, and going more to the creation of a dynamic partnership with the local communities, where the project and the community flourish together, where both create shared value through the project. And this is a critical idea, I think, through pilot strategy. We know from past experience in CCS world, but also in other energy technologies, that generally socially acceptable projects have these four characteristics. They create and promote effective methods for engaging and informing the public and the stakeholders, let's say public engagement. They are really locally embedded, and in the sense that they are very well integrated into the local context and the culture. They serve as a continuation with local structures in terms of local infrastructures, local economy, local vision, local values. It's not that disruptive in this sense. And also these projects usually tend to provide local benefits in terms of socioeconomic impact, but also in terms sometimes of local compensations. Taking this into account in pilot strategy, in our project, we developed this community engagement strategy, was mainly implementation, but also research strategy, with the idea of, and with the goal of listening to all the segments of our community, which is in this case, Belchite, the small area, and the surrounding locations, listening to all the segments, listening to residents, listening to stakeholders, through these five, let's say, tasks that we develop in the project, together with the technical team, the economic, environmental, and geological characterizations. We conducted a community characterization. We started and developed stakeholder interviews, semi-structured interviews with different sectors of the local community and the regional community. We implemented a resident survey. I will give more details. We develop also small actions to engage with the public through small groups, small activities. And finally, through the project, we developed and implemented this stakeholder committee, finally, where we meet regularly with the stakeholders to discuss several issues. So very briefly, but this was the starting point of our community strategy, community engagement strategy. Mainly was a characterization of the community, trying to understand the community context, the historical and socioeconomic background, community dynamics, local concerns, local aspirations, local values, and very important, previous experiences with similar projects or with related projects. This is always an important point. We did this with documentary analysis, with interviews, and with media coverage. Then we proceed with the interviews with the stakeholders together with the technical team. We tried to interview everyone with a relevant position in the local community. Of course, we were not always successful, but we gathered a good representation of society's members. We interviewed local government officials, members of the civil society, NGOs, community organizations, industry representatives, and regional authorities. The idea was to understand stakeholders' perceptions about the project, perceptions of the benefits, perception of the cost of the project, ideas, prejudices, everything they had in their mind about a potential carbon capture and storage project. That was that kind of map. We were interested in mapping all these perceived benefits, also the same for perceived costs. This is an example of some of the perceived benefits that we collected through the interviews, and then we try to explain them and try to get how they really view these benefits. We conducted a survey with residents. Here, it was a challenging task, but the idea was to provide information about CCS technologies and about a potential project in the area to residents, and then get their feedback on these technologies and these projects. We were also interested, of course, in measuring initial level of support and acceptance for the project, but also in general emotions associated to the project, perceptions of benefits and risks. And this was the quantitative data that we used to more or less measure the public sentiment. Well, this is just a very brief type of data that we got, but for instance, here we were able to measure acceptance, and we can find that in general in the community, as we survey it, and this was 1 year ago, but we found a neutral to positive attitude towards the project and a medium level of acceptance. We also conducted these small citizen engagement activities. In this case, it was a small activity with 10 participants. We had 2 sessions. We gave them information about the technology, information about the project. They took this information home. They came back, and we discussed many things: the emotions they associate with the project, the perceptions they have towards related to the technology, the associations they have with this kind of technology that is mainly unknown for the majority of the residents in the area. We also discussed the conditions for acceptance, which means what will need a project of this kind to have to be accepted by the local community. And finally, we had, through the project, we had stakeholder committees, where mainly this was a very important space for exchanging information. We gave them information about the project and about the technology. The technical team was always there. But more importantly, we listen to them. We collect data from them also, in the sense that we listen to their perceptions, their concerns. And somehow we were dealing with several topics through the project, from the perception of the benefits of the project, to the perception of the risk, to issues such as potential compensation measures were discussed in specific sessions. For instance, in this is a result from one of the stakeholder committee workshops, where the stakeholders had to categorize the potential risks of a CCS project in the area. Of course, this was coming from their knowledge, their familiarity, their perception of their risks, how they consider them important, non-important, and controllable, non-controllable. This is the kind of exercise we did. So yeah, to sum up, we have been using the pilot strategy project also as in a sense, as a social laboratory in the sense that we are trying to develop these methods for public engagement, but also because we are trying to understand community reactions to a CCS project in Spain, which is not totally new technology, but somehow very new, very emerging technology for most of the local communities in Spain. So we were focused on understanding our community. We have been working in pilot strategy to understand local values, to map residents and stakeholders' perceptions, views on the project and on CCS technologies. We have been using all these method to develop a two-way communication flow, provide them information when they need, provide them information in case they ask, and also asking them about their views. We have been using it, I think, quite successfully, but of course, you're never sure about this, but to build trust. So our engagement strategy is generally perceived, we think, as also as a trust building and legitimation building relationship with the community. Our position is also clear on this, that we are not trying to sell anything. We're just trying to engage with the community on this important project. And somehow these communities are serving as a living laboratory of how future projects, of future CCS projects, could or should be developed across Spain and generally across Europe. We hope some lessons we have from this project, also, of course, from past projects and studies, can guide future commercial projects facing similar challenges. We don't like to say problems, just challenges regarding social acceptance. Thank you.
Thanks, Christian. Richard.
Thank you, Christian. Thank you, Paula, and thank you to all the speakers. I'd like to just invite all the speakers to enable their cameras. We're going to move into the Q&A session. I'll take the opportunity to allow the microphone and cameras for all the attendees, but please, as a courtesy, remember to keep your microphones muted unless it's your turn to ask a question. What I'll say is, please use the hand raising function. We'll try to alternate. There's quite a few questions in the Q&A, so I'll take them in the order they arrived. So if you wish to ask an additional question, we can switch between them with hand raising feature. If I'm reading out one of your text questions and you want to follow up with it while one of the speakers does answer the questions, please feel free to jump in and contribute to the discussion. So I'll start with the first question that came in. So what is the storage capacity that you foresee in Tara CO₂?
Hello. Yeah, I can take that. So storage capacity, static storage capacity is beyond 140 million tons of CO₂. Our dynamic simulations are based on the base case, which is at a rate of 2 million tons per year. That could be scaled up, of course, but remember, it's an investigation permit. Our first task here is to drill and test injectivity. We are aware that the good quality of the reservoir, but it has to be tested. So answering long story short, capacity beyond 140, static. Dynamic, we are working on a scenario of 2 million tons per year.
Thank you, Francisco. There was another question about the data available to build models or 3D seismic surveys. I noticed that this has been answered in the chat, so you're all welcome to have a look through it. If anyone has a follow-up, again, feel free to raise your hand. Another question on here. I'll read it out because it was someone who left a comment very much saying they had to leave the meeting early, but just for the benefit of everyone, I wanted to highlight, the comment says, I wanted to highlight two aspects to be aware of regarding the onshore site. First, high formation water salinity means higher risk of water vaporization during injection with halite formation. A geochemical model could assess this aspect. Maybe it has already been done. And number two, the reservoir appears to be close to the Paleozoic basement with normal faults. It would be useful to check that basement fault orientation with respect to the planned pressure change during injection to assess the risk of induced seismicity, I suppose. May these faults become critically stressed. So I don't know if there's any comments on that might be good for the discussion.
So I will take the question of the salinity. Now we are on the stage of doing this geochemical assessment. It is not performed yet, and we have this risk, but it is already contemplated. So now we are in collaboration with Edinburgh University. We are performing this model. It's not done yet, but we are on this phase now.
And about the faults and the basement, we analyzed from the beginning in the case of Lopin, just in case it was a stopper. So we were very close to this possibility, and we rejected because according with the information that we have, there is no risk in the term of risk right now. That can be a stopper for considering this.
Thank you, Paula. There was also a question of specifically about the Lopin case, about large-scale injection and what is the expected pressures. There's an answer on there also provided by Paula, so thank you for looking through that. And there's an additional one that says, was there any changes in community perception of a CCS project? I suppose this is for Christian. So was there any changes in the community perception of a CCS project after the social engagement program?
Yeah, well, we still don't know because we're to implement the second survey the beginning of next year. So yeah, we will know it next year. Yeah, we still don't know if there has been some change in the local residents' perceptions. No.
So I will take the other question. So in Lopin case, the fracture pressure that is modeled with the geomechanical 1D experiments, that analysis, I mean, is 300 bars. And we are considering 90% of this fracture pressure as the upper limit for the pressure that we are going to apply. No? So the expected maximum pressure increase will be up to 280 bars. And does this impact to the seismicity? So we know that natural seismicity in Lopin is very, very small magnitude, always below 1. And the earthquakes that develop during 1 year recording are located very deep, 4 kilometers in the crystalline basement. And we don't expect, and the models are not showing that any impact on the seismicity in Lopin. No? For us, of course, for every project, it's a high risk that we need to pay attention to. But in Lopin, it seems that the risk is low. But as I said before, we are in the middle of the project, in the half of the project. More analysis and more studies are going to be done in this respect.
Thank you, Manuel. There's one additional question that came in. What chemical reactions between CO2 contaminants and the rocks were analyzed?
Well, it's the same, it's a similar question as the salinity. We are right now on this step of the geochemical assessment. So the model is not done yet. So we are on that. We are doing this, and so I cannot answer the question right now.
And also, I would like to add that we are studying the storage potential with no specific source. So we are considering CO2 pure right now for the models from the beginning, because we don't have in mind any specific source for being evaluated. That could be the next step.
Am I okay in saying that a lot of the results from these aspects that you've discussed will be posted as deliverables in the website? For the benefit of everyone, I'll put a link in the chat just now, which is a direct link to the website on the results page, where you'll see so far the public deliverables that have been made available, where you can view and download them. Coming on to the next, the last 5 minutes of the webinar, but there's one additional question that came in. Thanks to all speakers. How important is it to study the alterations in wettability of the rock during and post CO2 injection? Do any changes in wettability affect the long-term storage of CO2?
Hello. I think the wettability keeps the same. It's not as far as we know that at this stage, we think that it will be stable.
And another question, what is the impact of solids dissolved in CO2 on the permeability of rocks?
This is something that to be assessed. No? We didn't perform the geochemical model yet. And the affection of the reservoir quality with these impurities. No? Also, as Paula said before, we are now considering pure CO2. That.
Yeah, we did some preliminary tests in the first 20 months in the pre-selection phase here in the IGME. And the Bunstein is a sandstone. According with this test, it doesn't look a high alteration, so not really a lot of solids and precipitation can be expected. But, as Manuel said, we are still evaluating the geochemical model and it needs to be built.
Thank you very much. We may have time for just one quick question if anyone would like to contribute to that. In the meantime, I'll take the opportunity to say thank you to everyone. Thank you particularly to the speakers and to everyone for attending. A special shout out if you have attended previous webinars for the project. Thank you for sticking with us. Recording for all the previous 4 webinars in the series and for the initial webinar of the project are all available on the website. I'll put a link in the chat for the events page where you can find all of them. And the recording for this webinar will be made available in the next 24 hours or so. I invite everyone to visit our website. As mentioned in the first few slides, the project will run until 2026. So please keep up to date with other events, with news. Please sign up to the newsletter and follow us if you can on social media. We're live on LinkedIn and on X, Twitter. So thanks everyone, and once again, thank you for Paula, Christian, Manuel, Jesús, and Francisco, everyone for your presentations. And we'll hope to see you again for a future webinar.
Thank you.
Thank you very much.
Thank you.
Enjoy the rest of your afternoon.
Thank you.